And we are recording the session, and it will be available later for viewing. So just a couple of notes for providing the best experience in the Zoom client. So first, if you go to the video settings menu, if you have video, and if you turn off the Spotlight My Video when I speak option, that's probably best. Also, if you use the speaker view rather than the gallery view, that will probably work out pretty well. And please keep yourself on mute throughout. At least right now, we have quite a few participants. So if that remains, well, we have about 15 participants. If that remains the case, we will allow live questions. But if the number of people grows, then we may have to switch to doing offline questions. So the questions should be in the chat. Maybe we'll see how it goes with live questions, and if things get too chaotic, we'll have to make the switch. But okay, with that, Sharad?
Sure. Yeah. Thank you. Thank you. So let's get started. A quick question for you. There are a few people still I'm noticing who are in the waiting room.
Yeah, we're adding those. We're adding them.
We don't have to worry about it, right?
No.
Okay, very good. Perfect. Thanks everyone for joining us. Let me just close that window so that, okay. Is my window now clear? Like, is it okay?
Everything looks great.
Okay, very good. Let me just move the video around so that I can see my own screen properly. 1 second. Okay, that should be fine. All right. So yeah, so we'll have a 3-hour tutorial broken into 2 parts, hour and a half each, on advances in cryptography and secure hardware for data outsourcing. As a lot of you are already probably quite aware that this area of data outsourcing has been in our community now for a while. People have been working at it probably for close to 2 decades at this stage, and significant advances have happened. So the interesting thing is the area. So when this area sort of started off, maybe I should give you a small history and then sort of move on. So probably one of the first papers in this area were by Rivest on a thing called privacy homomorphism. I don't know if some of you have heard of it or not, but there was a very forward-looking paper which imagined the world where data would be outsourced, and sort of you want to do homomorphic encryption and homomorphic computing on top of it. And the solution may not have been ideal or may not have been the best solution that was possible. There were leakages in it, but certainly set up, imagined a world where basically outsourcing would be the normal, cloud computing will come around. Then this remained dormant for about maybe a decade and a half or 2 decades. And then it sort of took off with a couple of papers looking at, that's sort of when the cloud computing started off as well. So this area of cryptographic computation on top of cryptographic, let's say, representations became a big area for our community. I don't know if we thought that it'll last this long when this area started off, but this is one of those hard problems which is still probably more relevant even now and today as compared to when the area had started off, because there are a lot of challenges and a lot of activities both in industry and in academia. The interesting part is that a very large portion of the work in this context has shifted not just in database research, which still remains, but also the cryptographers have been very actively looking at different aspects of this problem as well. All right, with that, let me get going. Oops, where is this not? It's advanced slides. All right, perfect. So our tutorial will consist of essentially 4 parts. I will give an overview, and we'll kick off with an overview of the tutorial, sort of maybe spend about 20-25 minutes on that. We look at cryptographic techniques, especially focusing towards the new things that have emerged, which is the MPC-based methods and secret sharing methods and so on. So Shantanu will do a presentation on it. Maybe Shantanu and Anton, can you show your faces maybe one time, a video, and then turn it off? Would that work?
It should work.
Okay, cool. So that people can see who you are. I guess Shantanu, okay. So Shantanu will do a presentation on that. Then we'll shift to the trusted computing platforms and SGX. Anton is an architect among us, and we have been collaborating now in the context of, let's say, doing data processing on secure hardware. And we've learned a lot from Anton in terms of, let's say, the leakages that are there in, let's say, in the trusted computing platforms of today. So Anton will give us a little bit of that. Also project out and tell us what the future will bring, what are the activities going on and what challenges will remain, which will not be addressed in the hardware. As some of you might be aware that there are vulnerabilities in SGX right now. a lot of papers are written which sort of ignore that to some degree, hoping that the hardware will sort its problems out. But I think it'll be interesting to see what Anton's view on this particular part would be, as to which of these things will get sorted out in the architecture and the hardware, and which of the problems will remain and have to be addressed at the software level. Then we'll come back, and I think the main aspect of the tutorial is going to be, which is probably if you're giving this tutorial, let's say 10 years ago, the message would still have been the same, I think, that there is no silver bullet. There are lots of point solutions, and I think the point solutions, like the way I think Bush said once, 1,000 points of light. So there are 1,000 points of solutions that exist, but there's no single silver bullet in this context. And therefore, one has to, if you want to sort of solve the problem in general, we have to think in the directions where we try to leverage the best of secure solutions and map that to the application needs. And I think we'll kick off a discussion. I don't think we have a clear idea how this can be achieved, but there's been a lot of work which has happened, which is basically dancing around this concept of trying to fit the, let's say, secure representations to the needs of applications. Actually, some of this work sort of was a collaboration with Murat, which we had worked on together as well. So Murat, if he's there in the tutorial, he'll sort of see some reminiscence of that kind of work coming back again. So we'll talk a little bit about that, what we think is the way forward in trying to address some of the limitations of cryptographic solutions as well as secure hardware solutions. And I think we'll end with conclusions and open problems. We want this session to be more or less, at least to some degree, and let's see if it gets to be interrupting our plan, interactive. You can ask questions. I think it's either on Zoom chat or on Slack. The plan we have is that the person who's speaking, he probably cannot monitor at the same time Zoom or Slack at the same time, probably, but there are 3 of us. So we'll be the other person will be monitoring, let's say, Zoom and Slack, and sort of we'll bring the questions, interrupt the speaker, and sort of try to answer the question as we go along. Hopefully that should work out. All right. So let me begin with a very high level introduction. I'll go fast on this part because this community doesn't need an introduction to cloud computing at all. We live it every day. There are lots of advantages and of the cloud computing that we experience, whether it be the utility model, elastic computing, the ability to sort of have machines and have data centers and so on without having to manage them, without having to upgrade the software or to apply patches or do bug fixes and so on. And of course, one of the main draw of, let's say, cloud computing has always been cost amortization. So you sort of pay for only what you use and do not build, you do not have any startup costs to sort of start using machines and scaling up your applications. Now, from the perspective of this tutorial or for secure computing, we have to differentiate between different styles of cloud computing. So the simplest example is private clouds. And the idea, what we mean by that is basically data centers or clouds are sort of owned by an organization itself. So the level of trust one may have in a private cloud might be different as compared to, let's say, a public cloud, where everybody, it's like tenants. So people sort of come in, they use the machines and they go away. You do not control essentially who are the people who run your cloud for you and what happens to the machines which are sort of in the public cloud. So the level of trust might not be as high as it might be in, for example, in the private cloud. So public cloud is normally when we do refer to cloud, and most of the outsourcing stuff that we'll talk about will be in the context of public clouds itself. Then there is also a mixture, which is hybrid cloud. And hybrid cloud is sort of you can have some part of the data or at least a mixture of private and public cloud working as in a seamless sort of a manner. So you can shift your computation. For instance, one of the use cases of hybrid cloud would be that if you're trying to do some work on your private cloud and the computation goes beyond, let's say, what your machine power is, you might shift the computation to some part of that to at least the public cloud. There are several different ways in which you can use the hybrid cloud, but typically what we mean by that is sort of a mixture between the private and public cloud. All right. Okay. So for the most part of the talk or of the tutorial, the consideration we are going to go with is a public cloud model. So public cloud is a shared resource. And so data resides in these shared systems. And the administration of this data is not necessarily in the control of the end user or the owner of the data himself or herself. So since different applications share the resources, there are vulnerabilities that you have in the context of public cloud. I think one of the biggest problems that one faces, whether there is a challenge in terms of actual theft or not, is this perception of loss of control. So you do not control your infrastructure, and that offers obviously worries to people. These worries can be in the form of insider attacks. So basically a bad employee, a bad sets of employees in a public cloud or a rogue public cloud itself, vendor, could actually be stealing the data on the side. So there's a concern if you have sensitivity in your data, then sort of you do not want to, you want to protect yourself against the insider attacks. You don't hire the people who are running the public cloud, you don't fire them. So sort of you have to sort of deal with the issue of insider threats in this case. And then public cloud is sort of one location where a lot of data comes in from different people, and therefore it can be vulnerable to attacks from outsiders and miscreants and so on. So there are complexities of this kind. The other aspect of it is that if you're storing your data, and this is a big worry for certain situations, in certain contexts for sure. So public cloud has been known in the past, if organizations store your data, they could be basically vulnerable to, let's say, compliance to the government subpoena. So your data could be shared with let's say, agencies detrimental to your, let's say, not necessarily good for you, and detrimental to your organization. So people have concerns in that kind of loss of control. Now, this loss of control manifests itself in a variety of different ways. One of the aspects of it is availability. So the question is, you no longer control your resources. Will the system be available when you need it to be available, for example? You are shipping off the responsibility of this to the cloud. Usually availability is actually one of the things where it works out quite well, because largely the cloud would have a better, let's say, infrastructure and better people to manage your availability of the system. But that being said, if the cloud is not trusted, then availability could certainly be also an issue. Okay, and there have been cases where outages have cost customers a lot of basically credit and money and so on. Another challenge is integrity. So the question is, will the cloud actually do the right thing? If you ask a query to the cloud in the context of query processing, will you get the right answer or will you not get the right answer? Can they basically manipulate your data to your detriment? And the answer to this depends on the level of kind of data you have and the level of trust that you can have in the cloud. Often we'll assume that the cloud is going to be honest about what they do. They may be curious, but they basically will be honest, and the integrity problem might not arise. But in certain highly sensitive applications, integrity becomes a large challenge as well. Then there is the more pertinent challenge from the perspective of this tutorial, which is dealing with basically security and privacy. And the question is, will my data remain sensitive or not? So can we ensure that while the processing of my data pushes to the cloud in the outsourced model, but I do it in a way in which this privacy and security of my data is preserved? And there have been lots of breaches like basically the popular media is full of articles which sort of show at times when basically there have been data thefts from the cloud, or there have been insider attacks and so on and so forth, which have led to basically this whole aspect that loss of control is a big problem. And one has to worry about making sure that data remains safe. And the privacy of the data of the individuals as the security of the data that you store is basically maintained. So what's the solution? It's a sort of a rhetorical question. One of the answers which comes right away to mind is, okay, if you outsource data, encrypt it before you upload to the cloud. And the problem that we face is, if we do that, the question is, how are we going to sort of compute on the data? And one answer to this, which is a non-answer to a certain degree, though it will turn out as, hopefully you'll make a case for it very soon, that it's not necessarily a no answer. In situations, this is the answer. Is, hey, you store the cloud, you treat the cloud as a secure storage for you, a large storage for you, download the data and do your processing on the downloaded data, and then you sort of upload whatever results might be. So that's like the download model, trivial as it is. It is secure because, hey, you're not doing anything with there's no concept of a theft at this stage if your cryptography is strong enough, essentially. Now, this is not what we want to do. We want to be able to sort of do the same stuff or execute on the cloud itself. And the minute you do this, there's a whole bunch of like 2.5, 3 decades worth of solutions in cryptography, which is dealing with homomorphic encryption techniques where you can actually compute, or at least partially compute certain things on the cloud side. So the talk and the tutorial will focus a little bit along that direction as well. So you store your data in an untrusted public cloud. You have a query in an encrypted fashion, and you send your queries there. The queries are executed as much as they possibly can be, hopefully completely. And what you get is an encrypted answer, which you then have your own key, and you can sort of open up the answer and you get the results. There are, even for this model that we sort of have listed here, there are several different variants of the model. This model sort of shows that the owner of the data and the querier is the same person or same entity, but that might not be the case. I could be an owner of the data and somebody else could be a querier. So there are variations of the technique that come in just from that perspective of whether it's a single querier or there are multiple queriers, and whether it's the owner is the same thing as a querier or not. The other alternate solution, which is also what we'll focus on, and this is with the advent of SGX, for example, in the market and Enclave, this has become a big thing, is basically having this aspect of secure computing. So imagine that there is on the side, on the public cloud, there's this agent of yours just sitting there, which is secure, which is tamper-proof completely. So the question is, you take your data, you encrypt it, and you give it to the, basically using non-deterministic encryption of some kind, and you push it to the database in the public cloud. And when you send a query to execute the query, the hope at least could be that, hey, as much of the query as you can execute in the encrypted domain, that's great. But if you keep getting the notifications, I'm not sure this is relevant to this particular, it's not, okay. So, all right, so if you keep getting once the data is in the encrypted form and you want to run a query on top of it, so you execute as much of the query as you can in the untrusted sort of a cloud setting. But when the need arises for you to sort of open the data up, and because the computation cannot go any further, you go to a secure enclave. This is your agent of a user or the owner, which is tamper-proof, so that untrusted cloud cannot open it up. And the data goes there, it gets decrypted, your processing continues, and therefore it's like a collaborative processing between the SGX and the untrusted server itself. Now, in this case, we don't need homomorphic encryption, though you can mix homomorphic encryption obviously along with SGX, and that's interesting because you can sort of push as much as you can on the untrusted domain, and then you can get the benefit of both worlds essentially. That being said, there's no reason for, you can just do a computation on a secure hardware by itself. All right. So what are the kind of attacks that happen in the data outsourcing situation that one has to worry about in designing approaches? So remember, we are trying to design approaches either for a cryptographic approaches that support essentially query processing on top, or we are using a secure hardware on top of which query execution can happen. But these techniques, what do they have to guard against? That's the question. So there are several possible attacks that are there. So you could have a ciphertext only attack, where basically a ciphertext itself reveals, let's say, information about the data itself. So for example, as we'll soon see, there are techniques which basically do deterministic encryption, where let's say every value gets encrypted in exactly the same way. So that's deterministic encryption. So the cipher representation of a value of two records containing the same value is exactly the same. Now, obviously that will reveal the distribution, for example, of the data. There is other techniques called order preserving encryption techniques, or any property preserving encryption techniques that are there. They reveal certain properties of data. Now, and the adversary can gain this insight from the ciphertext because of the choice of the ciphertext that you've, or the encryption technique that you've chosen. Now, the problem that we often face is that most of the work in cryptography sort of deals with property preservation, which is reasonable, which is fine. The problem is that it's not clear from a semantic perspective what that actually means. So if I tell you that the technique of mine will reveal order, well, what's the implication of that? So what will I actually lose, given that the adversary is able to learn the order between things? So sort of cryptography ends there, and the definition of security sort of ends there. But really there is a semantic question which is sort of further on, which is, hey, what happens in case you, in case the property that you're after is violated or is revealed? Okay. There are other attacks. So attacks could be basically in some properties. You can also reveal the, so I already talked about the distribution attacks, like which is, for example, in the case of deterministic encryption. adversary might know the workload. So the adversary may know what kind of queries you run. For example, in the context of keyword queries, they may be able to figure out, hey, most of the queries correspond to, let's say, Google, or most of the queries correspond to something, or there is a correlation between time of the query and the actual query. So adversary might be able to learn that, and from there, they might be able to learn something about the data as well. Another very common attack, which sort of a large number of techniques do not guard against, is output size attack. And in the output size, even the strongest notions of security that we'll sort of today talk about, you'll see that they still remain vulnerable to output size attacks. So and this is a difficult problem to solve to a certain degree, because if you want to run a query on the cloud side and you want to get an answer, if one can infer from the answer size what the query was and then what the data was, you might be able to guess something at this stage. So output size can actually reveal data as well, or you can lead to inferences. And preventing that is sort of a little complicated as well. Then there is access pattern attack. So adversary gets to see the access pattern of what's basic in answering the query, what kind of objects were in the memory, what part of the disks were accessed, and so on. And that could lead to inferences as well. Then and this thing list goes on. Like there are a lot of different other attacks as well. So search pattern attack is another one of these things. All right. So basically the point being that given these attacks, along with adversarial background knowledge, it can reveal essentially secure data. The problem is that we can talk about, so first, as I said, there's going to be no silver bullet. So we'll end up having to reveal something or the other. The question is, when we reveal certain aspects of the data through such attacks, for it to be harmful, usually adversary has to have background knowledge, and then that'll reveal a secured property or whatever it might be that you are trying to hide. The problem is if you don't explicitly model adversarial background knowledge, maybe it's not that clear in these techniques as to whether the representation that you have or the particular choice of cryptography that you use, which let's say reveals certain aspects of the cryptographic representation, is it good enough for you or it's not good enough for you? And that remains one of the challenges, the way we see it, of decide if you have to choose among different mechanisms, what should you be guarding against? And that depends a bit on the modeling of what the adversarial knowledge might be. All right. Typically, as I already said, the adversarial model usually can be one of the two things. Either the adversarial model can be assumed to be malicious, in which case the adversary is trying to sabotage the data and the computation, or it could be honest but curious, in which case the adversary is passive. He's observing the data as it's flying by and is trying to make the best guess of what the data might be to use it to their advantage at some level. But they're not necessarily trying to maliciously change your computation itself. So there could be as active or passive adversaries. Passive adversaries just watch things as they go by, and the active adversaries sort of inject new things. I'm wondering, let me stop for a second. Is there any questions at all? And I see something in the chat. Oh, are these, okay, the question is, are these attacks exhaustive? Is there a notion of enumerating all possible attacks? Are there papers about that? I don't think the answer to that is that they're exhaustive, the ones that we listed. These are commonly what we end up basically guarding against, or cryptographic techniques guard against. I don't know if there can be exhaustive list of attacks in that sense, but there are papers which deal with attacks. I think Shantanu might be able to later on address that issue and point you specifically to a paper which is on attacks. There are some papers on that. And in fact, books sort of contain that too. All right. Let me close the question. All right. So let's see. Okay. So the question is, before we sort of start off further in discussing cryptographic techniques and how they work and so on, and the secure hardware techniques, we need to sort of sit back and look at first, how do you define the concept of security? So how will I know if my system is secure or not? Now, most definitions of security have been traditionally they're very binary. Either a system is secure or it's not secure. Like that's the mindset in which you sort of design things. And that had to be adjusted given that there was no silver bullet. So we had to adjust that to the context of leakages, because we want to allow like certain types of leakages, but not certain other kinds of leakages, or protect ourselves against certain kind of attacks, not certain other kinds of attacks, and so on. But if you think of security, largely security is defined in the context of semantic security. And what that means in the context of messages or networks, messages. So what semantic security refers to is that access to a ciphertext does not provide any information about the plain text other than what the adversary already knows. So that definition is that, hey, if I know ciphertext, it will not help me in any particular way. The problem with semantic security is it's sort of, if you're trying to come up with a protocol or a encryption mechanism, it's sort of difficult to prove yourself to be semantically secure. So there was a very nice piece of work by Shafi Goldwasser, which was basically about indistinguishability. So what she showed in that work was that semantic security is equivalent to indistinguishability. And roughly speaking, indistinguishability, it means that the adversary cannot differentiate between two ciphertext. The fact that indistinguishability is sort of related to semantic security, I'm not sure if it's that obvious or not, but let me give you intuition maybe, and let's see if that helps. So imagine that you have a database in which the adversary knows that there are only two records which have exactly the same representation, everything else is distinct, right? So if I now know that these two ciphertexts refer to the same plain text, then I would know the actual value as well. So the ciphertext will then give away the plain text. So you can sort of see the connection hopefully between the two of these definitions for that matter. So in this example, with the adversarial background knowledge that there is only two records is exactly the same value. If that knowledge existed, then if you're not indistinguishable, you'd also not be semantically secure. You'll be able to guess and infer the value of the object, right, in this example. The reason why indistinguishability is nice is because it is sort of easier to prove using a real ideal game, and I'll give you an example of it in a second. Now, these definitions of security were done in the context of basically encryption. For them to work in the context of, let's say, queries and retrievals, especially when there are leakages that could occur, people had to redefine these notions. And there was a very nice piece of work by Rafi Oritsky at UCLA with Reza Kratmola, which sort of went in that direction. So let me give you intuitions to how these things are proved before Shantanu goes in and sort of talks a little bit more about the techniques. So here's the example of, so this is one of the more criteria we often use for dealing with security in the context of approving security for encryption techniques for query processing. So imagine that there is an adversary, which is this guy here, and there is the user who's the owner of the data. And the way we'll sort of prove that something is basically indistinguishability under chosen keyword attacks. This is the common model of attack that we sort of consider. In this case, there are two types of attacks. One is the keyword attack. The queries that you end up asking are fixed, whereas there could be adaptive as well. So this is not an adaptive model. This is the other one. So essentially, indistinguishability under this attack is normally what we'll use for honest but curious adversaries. So imagine I have a database D0, which the adversary generates. And what the adversary does is he sends the data to the owner. The owner encrypts the data, sends back the data to basically the adversary again. Adversary generates a set of queries, and there's whatever the trapdoors are, whatever the way cryptographic mechanism is for sort of asking the queries, the user, the owner of the data sort of does that, and he sends back the queries to the adversary. So this way, this is based on the real data which the adversary actually already knows about. So the adversary knows the representation of the queries, the data, the encrypted representation of the data he has, as well as the queries. Now, in this situation, the adversary will get an adversarial view of when the query processing happens, which will be in the form of maybe access patterns, search patterns, output size, whatever the adversary sort of learns about from his logs by executing the queries that have been sent after encryption by the owner himself. Okay. The second part of it is actually the part which is now in the simulated world. So now the same thing, the data D0 is sent by the adversary to the owner. The owner has knowledge from the real execution of D0 in the past. The adversary has sent the leakages that happen, all the access patterns, search pattern, and so on that was observable by the adversary. And what the user does is he takes D0 and he takes these leakages and these patterns, and he generates essentially a fake data, which is D dash, with the same leakage, exactly the same leakage as before. And now there is this, let's say this data is D dash, so you have got D0 and D dash. So the user, essentially, or the owner, randomly selects one of these two things, either D0 or D dash, and he sends back D0. Let's say this is the encrypted representation of D dash. He sends back the encrypted representation of D dash back to the adversary. So D dash is either D0 or some other database created which has a similar leakage pattern as that of D0. And the question is, the adversary sends the same set of queries to the user, which he had in the past, because we are not dealing with the adaptive plain text attack, but we're choosing the chosen keyword attack, but not the adaptive attack. The user encrypts them back again with the appropriate trapdoors and so on, and the adversary can now observe the basically whatever the adversarial view of this state of execution of this query could be. Now, if we can prove that the adversary cannot guess if the data D dash is either D0 or a simulated data with any probability, anything much more than half, in this case, the technique is going to be secure. The technique is indistinguishable. So this mechanism of proving is used very often in the context of basically proving that your technique is secure against basically attacks from proving indistinguishability of security of encryption technique in the context of query processing. Okay, so moving on. So the techniques we'll talk about or encryption techniques, they sort of, if you think of, let's say, the different layers of a database system, from storage to processing to basically applications. So it sort of maps over to the different layers of the cloud, like infrastructure as a service or a platform as a service or basically application as a service or software as a service. There are different techniques for basically cryptographic techniques that have been dealt with at different layers. So for example, at the infrastructure level, usually what our goal is to ensure that the data is at rest is encrypted. There's a lot of work which sort of builds on query processing and so on.
Is it me or others can hear Shad?
No, Shrad seems to have dropped off.
Went off for me as well.
Shad, you were cut for a minute. Can you hear us?
Yeah, I can hear you. Sorry, I'm not sure where I got cut.
I think like 1 minute,
Just
not 1 minute. Yeah.
Yeah, just the last
Did you
30
go to
seconds repeat.
All right, so from this slide, from cloud layer slide?
Yes.
Okay, all right. So now all we were saying was that encryption can be done, or the secure processing in the cloud, it's done at every layer, at the infrastructure layer, at the platform layer, and the software layer. And there are different techniques sort of which are implemented at different layers. So the goal at the infrastructure layer, if you saw, sort of is primarily to ensure that data at rest is basically, one second. So it's the data at rest is, when it's rest, it's encrypted, but when it's brought back into memory, then it can be basically in plain text form. And there's some work along the direction of how to do query processing on top of it. Actually, there's a paper which Murat and I did a while ago in BLDB, which sort of addressed that very issue as well. Now, most of the talk that we'll do today is sort of at the level of data processing there. So we're going to be talking about secure MapReduce, basically, and we'll also talk about secure SQL executions and so on. So this is sort of at the platform layer. There's also work at the application security layer. So imagine that the responsibility of secure execution is not necessarily even at the platform layer, but becomes at the application layer. And that adds another complexity or interesting aspects to the problem, because you have limited control over what you can do in terms of cryptography. Like you cannot force a platform to implement your protocols, for example. But then, so the only control you have is that sort of controlling at the level of the application. And there are actually interesting developments along this direction as well. There's some work we did. There's actually one of the students who did work in this direction on application security. He started a company called Gabble Cloud, which I'm hoping is doing well. It seems to be doing okay as far as I can. It's surviving at the very least. So there are people who have done stuff along this direction. There's also a system called Spark, and what they were doing was trying to do document sharing at the application layers using cryptographic techniques to sort of ensure that the documents, so you can do Google Doc or whatever it is, your favorite document sharing sort of algorithm or protocol. I think the one that document sharing uses is this operational consistency. So implementing that while ensuring basically that the document remains encrypted. So there's work along that direction as well. So essentially, people have looked into cryptographic techniques at every layer of the system, at the level of infrastructure, at the level of sorry, I think I went too fast or something. Yeah, at the level of infrastructure, at the level of platform, at the level of applications. Today, I think we'll focus primarily on the second one, which is at the at the level of, let's say, platform, or at the level of doing SQL processing on top of databases. Okay. And in this context itself, from cryptographic perspective, there are a huge bunch of techniques which are out there, ranging from fully homomorphic approaches to partially homomorphic approaches to searchable encryption techniques. And I think Shantanu will give us a little bit of an introduction to each of these different things, or at least to the searchable encryption part of it. Homomorphic technique, so by fully homomorphic, just so that we have it covered, computation can be, almost every computation can be expressed as essentially a combination of addition and multiplication. So if you can do addition multiplication in a secure way in an encrypted representation, then you can sort of do any computation in a secure way. So people have developed fully homomorphic approaches. The problem is it's extremely inefficient. Partially homomorphic essentially refers to either additively homomorphic or multiplicatively homomorphic, and these are far more efficient compared to, let's say, fully homomorphic techniques, but you cannot do everything you want to do in partially homomorphic techniques. Specifically search, there's a lot of work in the context of search, and here I've listed, I think, 5 or 6 of these examples, but I think Shantanu will show a slide which is like around 40 or 50 different encryption techniques in this direction. I think he'll present a few of them. All right. The key message here is that there are lots of different approaches from cryptography. They offer different levels of security. They support different levels of operations. Not everything supports all the operations, and they offer different spectrums in the efficiency. So again, builds back to the same point, which says that there is no silver bullet. There are lots of, let's say, trade-offs in this domain. More recently, there's been a lot of interest in multi-party computation and secret sharing mechanisms. And one of the reasons, and there are a listing of the techniques and systems that have been built around recently, which are along that direction. Roughly speaking, Shantanu will again go a lot more into detail how this thing works. But the idea is that imagine that there are several clouds, and let's assume that they don't all collude. So a significant subset of them do not collude with each other. If that is the case, you can take an object or a data and you can sort of split it over multiple of these clouds, and the computation that happens, so you can sort of do, so no cloud ends up learning much about basically about the data itself, but they can collaboratively answer a query. Now, either the collaboration can be in a communication sense, so the different clouds can talk to each other, and most MPC mechanisms sort of assume that the clouds can talk to each other. They don't collude, but they can sort of have a protocol which will enable them to exchange data and then collaboratively answer your question. There's a secret sharing mechanism which sort of don't even require basically people to communicate, the clouds to communicate. They communicate only through the basically trusted private server. So the private guy has to do some work to basically generate the final answers from the execution that happens in the different clouds. And one of the first works in our community, which sort of took on secret sharing and developed a database technique and doing SQL processing on top of it, was by Amar and Divi. So they had a very early paper on, I think, trying to use secret sharing in this context. But secret sharing itself is really old sort of area. All right. The advantage of secret sharing in MPC is they're far more secure compared to, let's say, property preserving encryption techniques or searchable encryption techniques. First of all, these techniques they will be secure against access pattern attacks, and they are information theoretically secure. So in other words, even if cryptography, even if cryptography breaks and you are able to sort of break into cryptography itself, now here we are sort of taking a secret and dividing into multiple parts. So as long as you do not have a collusion between the clouds, you cannot break the scheme even with a quantum computer. So they're quantum secure in that sense. So it's higher level of security. The problem with secret sharing in MPC is that they're extremely slow. So if you sort of think of it, they're in order of 5 to 6 order of magnitude expensive compared to plain text processing. and for good reasons. Another problem that we face right away is that most of these MPC techniques will be non-indexable. So they will be linear scans. They will have to go through the whole data and sort of execute the query in the entire data as well. So here's a sort of a comparison of security threats to different cryptographic techniques. We talked a little bit about this. So full download is the gold standard as far as security is concerned. It's supposed to be the bad strategy, obviously, because you're sort of just using the cloud for storage and not for any other purpose. This will be secure against data at rest, ciphertext attacks, output attacks, skew, workload skew, access patterns, and so on. And then you have schemes such as deterministic encryption OPE that are basically not secure against anything for that matter. So you still may want to use this if the user is okay with it, in the sense that if you don't care about, let's say, ciphertext indistinguishability or a or an adversary learning distribution of data, if that doesn't lead to anything at all, then it's fine. You can use it. In fact, a lot of systems are built around something like that. As an example, if I know correctly, the SQL always encrypt system sort of uses deterministic encryption as well. So there are systems that are built which have this, but they just don't offer any great security. Then you have non-deterministic encryption techniques, which you learn, and searchable encryption techniques are non-deterministic. So they offer ciphertext indistinguishability, but they may not be secure against other attacks, and so on. So the more secure, the largest secure executions are things like multi-party computation. They are secure for data at rest. They are also secure against access pattern attacks, but they are also vulnerable to output size attack and workload skew attacks. So if you have to be really guarded against, let's say, output size attack or workload skew attacks, you'll have to add some more stuff to these algorithms to make it even more complex than they are. Okay. Now, if you think of cryptographic techniques and think in terms of how do you design techniques to fit your application domain, there's several thoughts that one has to consider. Of course, the first question that will come up is the level of security you want. So how much security does the scheme offer? What's the requirement from security? What do you like? Are you going to be willing to sort of allow some leakages or not? That's obviously first consideration. Efficiency is the most obvious second consideration, that you sort of have to, how expensive will the solution be? There are other things, which is generality. So will the technique sort of implement your operations that you want implemented? Like maybe your workload does not require anything more than selection. So if there are no joins, maybe you can exploit that factor. If there are joins, then you know they're going to be in trouble in cryptographic domain. So there are a lot of these considerations of efficiency, generality, and security, but equally important are the other aspects too. So the two other aspects that is we'll see as we go down the road, you'll see this today, is the question that comes up is that is the dynamic operation supported or not? So a lot of the schemes that you have are one-time schemes, they're not dynamic. So you create a data set, encrypt it appropriately, send it to the cloud side, and then you can do query processing on it. But you cannot update things, you cannot change things. Now, depending on the application, that might be okay or might not be okay. Another consideration is the client-side execution. So a lot of the techniques we'll see require some degree of execution at the client side. Almost every technique will require you to basically decrypt at the client side, but do you have to do more? Do you have to do some filtering? Do you have to do some query processing on top of the client side? Those are considerations that you have to care about as well. And this depends on what your infrastructure on your side is on the client side. So a good solution or solution that sort of meets your requirements, you have to consider all these different factors and probably more to sort of figure out what the right solution for you might be. Okay, so besides cryptography, we sort of talked about exploiting trusted platform as a second alternative. Now, even here, exploiting trusted platform, there are at least two different styles of approaches that you can use to sort of exploit a trusted platform. The first example listed here is a hybrid cloud scenario. This is some work that went on, as I mentioned earlier on, between Murad's group and my group here as well. And the thought was simple-minded. And the question was, okay, if you want to compute on a public cloud and ensure still, let's say, security properties, one simple-minded way of doing this would be keep your sensitive data to a private cloud or private site, basically, and into your trusted, let's say, platform, and only outsource the part which is, let's say, non-sensitive. Obviously, there's a question of how do you decide what's sensitive and what's not sensitive. There's a hidden problem right there. But imagine you could, then you can sort of outsource only the non-sensitive part of the data to the public side. And then you can execute your secure computation collaboratively between, let's say, public side and private side. Another way of saying the same thing could be that imagine your data resides on the public side, which is encrypted. If you want to or need to sort of open it up, you bring it back to the private side, and then you can decrypt it and use your private compute machine as a trusted machine and sort of continue the execution from there onwards. So both these approaches sort of make sense. And this is the example of hybrid cloud setup, where security can be part of the hybrid cloud. It's part of the solution. Hybrid cloud can be part of the solution for secure execution. Instead of sort of bringing data back to you yourself, to your private machines, maybe you can have an agent, which is where the SGX or secure computation comes in. Actually, the work here way before SGX was, there's a very nice project from Microsoft called Microsoft Ciphertext, which probably set a lot of the current thoughts as to how we go around sort of executing queries using exploiting secure hardware, which went in. And I think Ken was part of that, so he's in the group here. So this work with Ciphertext is a very nice piece of work as well. And more recently, with the advent of enclave technology and with SGX, this research has become pretty mainstream, and you'll see a few examples of this. I think Shantanu will discuss a little bit about OPE as we go along, and maybe enclave DB. Okay. So there are several challenges, and a lot of these challenges are actually identified in the early work in Cipherbase itself when you're using the trusted platform. So for example, whenever you have this aspect of, let's say, computing in this heterogeneous environment where there is a part of the thing is trusted and part of the thing is not trusted, whether it's actually, let's say, using a FPGA technology or SGX, or for that matter, even hybrid cloud, the question is you have to sort of minimize the data movement, because the expense of this will be dependent on how expensive the solution is. It will depend on the amount of data you have to move between the platforms themselves. So how much data is being moved from trusted to untrusted platform and vice versa? So that's obviously a question that comes in. And you have to be extremely worried about this, because movement of data, which sort of reveals to some degree access pattern, could lead to leakage. So you have to sort of make sure that the movement that you do is done in an oblivious way, that there's no leakage whatsoever. And this complicates life for us, or obviously this design solutions for that matter. Then there are other challenges too. Like for example, as I said, the trusted hardware today is vulnerable to side channel attacks. So, and I think Anton will go a lot more deeper into this issue very soon. And there are not just side channel, there are several kind of attacks, from the cache line attacks to register attacks and so on. So there are lots of different complexities in this case. Usually trusted hardware has a smaller footprint, and it is more costly to compute on trust because you're doing decryption and then executing. So security, even though it's implemented in the trusted hardware, comes at a certain amount of cost. The cost probably is not as high in the sense of, let's say, just pure computation. The reason why it gets to be very costly is because you're wanting to have the oblivious execution. So protecting yourself against the leakage through movement of data is what contributes very significantly to the cost of the trusted hardware platform as well. Okay. So before we set up and sort of learn specifically and go into the details of the techniques and so on. So here is something to keep in mind. So here's an example where we are using 4 different technologies. This one is basically plain simple clear text execution. I don't recollect if this is on Postgres or on which database system, but it's a real experiment which was done, I think, as of yesterday itself. I think repeated yesterday itself as well, just to make sure the numbers are correct. So you're doing this on clear text. You're doing this on searchable encryption technique. There's a specific searchable encryption technique that we've chosen. You're running this on OPE, which is an implementation of SGX, and you're doing MPC computation. And to get an idea as to how expensive things can be, roughly, and this query that we're running is selecting 8 rows from a TPCH line item table of 1 million rows and 7 columns. So it's a very simple selection query, that's it. So roughly, if it takes, let's say, 10 to the power minus 3 seconds, basically on clear text, if you look at MPC, it's taking about 1,000 seconds. So there's an order of 5 to 6 at least, which is sort of right there. Likewise, if you look at, let's say, SGX or opaque implementation, it's taking roughly 10 seconds. So it's still an order of 3 or 4 order of magnitude difference between a hardware solution and a secure hardware solution and a clear text solution in this setting. And if you look at searchable encryption, this is about 2 orders of magnitude. So I think you should keep this in mind as we go forward, because this will play a very, very vital role in selecting what techniques you use. Okay, so I'm coming towards the end of the first introductory part of the talk before we go into the techniques and details. So here's a question that we have to ask ourselves. And this has been a challenge which has been open for the last 20 years, and we still don't know how to solve this properly. The question is, can we design an outsourcing solution that can simultaneously be efficient and secure? Actually, I should increase these demands to a bit more. Not only should it be efficient and it should be secure, it should be updatable as well. It should minimize the client-side execution and so on. So whatever we listed, or we want all the good properties of what we desired of a data outsourcing solution. And the question is, does such a solution exist or not? And the answer to a certain degree is probably there's no single solution that exists, but maybe if you can take a bunch of different solutions and you can split your computation across multiple different solutions, maybe you can come up with a overall solution, polystore kind of a solution, or overall solution, a mediated solution, which might actually work in this setting. And that might provide the right blend of, let's say, properties that you require of secure execution while maintaining efficiency and so on. So one of the things that we have been looking at in our group has been, and actually this work started off a long time ago with Murad as a partner in this particular thing, is looking at basically partition computing. So let me give you an idea, a little bit of an idea of it. So the concept here, and I think the concept can be generalized most likely, but the concept starts with this concept, with this issue of sensitivity, different levels of sensitivity of data. So imagine I have data which is, and in the case of, in this example, let's just say there are two levels, either data is sensitive or not sensitive. So we can identify that some parts of our data is not sensitive and some part of the data is sensitive. How is this done? Well, it depends on a lot of different things. Sometimes it can be done based on policies. Actually, if you sort of read the literature, which is the, let's say the popular literature on cloud computing, a lot of companies go through this anyway in making a decision in terms of what they can outsource and what they cannot outsource. So they sit back and then say, okay, something is outsourceable if basically loss or theft of it will not basically bring back the operation, stop the operation completely. So they have to make a decision of this kind as to what they consider to be sensitive versus not sensitive at some level or the other. So there are, so the assumption we are sort of making is that this argument that different types of data have different types of sensitivity requirements can be generalized, or it can be done. In this example, we are just dealing with sensitive and non-sensitive. So if we do this, so imagine the red ones are sensitive and the green one is essentially non-sensitive data. So a security goal, if we want to build a technique, will boil down to two things. One of them is non-linkability. In other words, in the execution that happens, however it happens, the adversary should not learn the relationship between any encrypted data and plain text data. So the green is the plain text. Let's assume that it's not sensitive, so I keep it in a plain text fashion. Red is sensitive, so I keep it encrypted. So adversary simply because of execution should not be able to tell that this green is related to this red. And likewise, ciphertext indistinguishability, which is the same property coming in that we learned earlier or talked about earlier. Given two ciphertexts, we obviously required that the two ciphertexts should not be connected as well. The adversary should not learn a relationship between these two guys. So if we can get this kind of a solution, which basically meets these requirements, that would be a solution that would potentially, so here, since this, at least the green, which is the non-sensitive data, can potentially be in plain text form, we may be able to scale up our technology quite a bit. Now, obviously, this will work much better if a large portion of your data is basically non-sensitive. But on the other hand, if the most data is sensitive, then obviously this partitioning in this kind of fashion will make, in this dichotomy, or just the differentiating between sensitive and non-sensitive might not be good enough. On the other hand, even if it's, so this red could be different colors of red, essentially, which are different levels of security required for different parts of data. So you can exploit this aspect to choose specifically what kind of cryptography you want to support. So I think we will get, time permitting, towards the end of the talk, we'll get back to this problem of how data partitioning can be used and to set up a challenge for the community, and hopefully there are PhD theses sort of written in that. With that, I'm going to come to the end of the first part, the introductory part. The plan next would be to hand over control to Shantanu to talk about cryptographic techniques based on basically encryption as well as secret sharing. After that, it will be to go to Anton for trusted computing. Then we'll come back and we'll go, depending on the amount of time we have left at that stage, a little bit more in the path where we don't know much about, which is data partitioning yet, and how to make it work. But we'll lay out a chart. Hopefully we'll lay out some initial solutions. We have a couple of papers so far in this area more recently, and we'll sort of lay out what the current thinking in this direction is. So with that, I think the introductory part is done. I don't know if it. I'm hoping it's. I'm still connected, and people are able to listen to this.
Yes.
Now I share my screen now.
Yeah. So before we do that, are there any questions that we need to answer before we move on? Okay. If not, Shantanu, I'm going to stop sharing my screen. And I'm going to stop sharing my video. So you can share video and screen.
Okay, so can you see the screen now?
Yes.
Yes.
But you can see a video though.
Great.
Okay, so now I will continue with some cryptographic techniques, that how they work, and some secret sharing based techniques. There are several cryptographic techniques. In red color, you can see that academic and industrial paper written on different cryptographic techniques like searchable encryption, bilinear map, OPE techniques, homomorphic techniques, and several papers on secret sharing like accumulating automata, verifiable secret sharing, homomorphic secret sharing. And on the right hand side, you can see a system developed based on these techniques. So based on encryption techniques, one of the famous system is Cryptography developed by POPA, and then mOPE is also by MIT. Then Microsoft developed Cipher-based system, and others, 0DB, CryptDB is also from MIT part. Recently, we saw encrypted key value store, and then some industry also used encryption-based techniques like Microsoft always encrypted, Oracle, Aurora, and MariaDB. Same thing is for secret sharing based systems. So there are some academic systems, and several industries are also working on developing secret sharing based systems. So I will cover not all the techniques, I will cover some of them, and these techniques are shown in the green color. So first, what are the challenges here? Suppose I am giving you a relation, and on these relation, normally I want to execute selection queries, join queries, and aggregation queries. So our objective is to execute these queries in secure manner on the outsourced data. So in order to do this, the very basic technique is searchable encryption to select a row. This paper was introduced in 2000, and this was introduced for the key value system. But we can use the same technique for the databases. So suppose there is a word WI, and I want to first outsource the data. So first, how can I outsource the data, and then how can I access the data? So first I take the word WI, encrypt it using a deterministic encryption with a key K. Now this word EKWI, that is encrypted word WI with deterministic encryption, this will become the trapdoor, means the encrypted query whenever I will search for this row or this word. So now for the encryption part, first I need to partition the word into two groups. The left hand side will contain the n minus m bits, and the right hand side will contain the m bits. So I am denoting as li and ri. On the li part, I will perform a function with the same key for the data used for the deterministic encryption, and it will give me some value, let's say ki. Now I take a pseudo random string. On this string, I will perform the function with the key that is generated from by implementing the function on the n minus m bits. It will give me a different value, that is ti. Now I mix all these values, and this will give me the ciphertext, and I will outsource this thing. So now the bottom corner is showing the what I outsource to the cloud. Now if I want to search, so the user will give me the deterministically encrypted the query trapdoor. And now, so the idea of this technique is that if I am giving you two words A and B and perform the XOR operation, I will get the third word C. Now in between all these three words, if I perform XOR, I will get the third word. So on this idea, the searchable encryption can search at the cloud side. So here is the encrypted keyword that is given by the user, and encrypted ciphertext. Now first we partition both data and query keyword into n-m bits and m bits of the data as well as the ciphertext. Now we perform the same function that we implemented at the time when we were outsourcing. So the cloud will implement the same function with the key ki. And now it will we need to XOR these two things. So the thing is to note down here that previously we got SI by XORing some other values. So the thing is to note down that previously we got SI by XORing the value of by implementing the function on LI, and now we got this even value. So even value will give me the exactly same value that I got at the data encryption part. So based on this thing, I will get another value that is TI. So now TI is the same value that I got at the time of data outsourcing. Now I need to match these two things, that the right m bits of CTR, this is equal to TI or not. If they are matching, then I can find, okay, this row is matching. Otherwise, this is not matching. So I need to check entire data to match the word WI. So here are some advantages and disadvantages of searchable encryption. So first thing, searchable encryption doesn't reveal anything before the query execution. But whenever the query execution happens, it will reveal everything because it needs to check the entire data, and then it will also reveal the access pattern. So based on access pattern, it will reveal everything. And another thing is disadvantage of the searchable encryption is that it needs to linearly scan the entire data. So there is no support in this particular technique. There is no support for this indexes. So now the question is this: how we can design an indexable searchable technique? So before going to see any indexable searchable techniques, there are several questions that we need to see. So first thing is that in what happens in the searchable encryption techniques, the cloud will create the index, and then the user will create the index, outsourced to the cloud, and cloud will maintain the index. And based on the query keyword, the cloud will traverse the index and give you the answer. So this is the basic mechanism of the index. But now the issues are this: who will generate the index? The first issue is the generator of the index. Each user is every time will generate the index and outsource to the cloud, or the server can generate at his side. Then the index traverser, how the cloud can traverse the index. Is it the interactive mechanism or the non-interactive mechanism? Means the cloud can traverse the index by its own. And the third question is index update. How the cloud can update the index. Is it allowed that cloud can update the index, or it needs again the user interaction to update the index, or the user needs to again rebuild the entire index and outsource to the cloud? We can, based on these questions, we can classify the indexable searchable encryption technique into two criteria. First one is the early approaches. So in the early approaches, database owner generated the index, and it required the interactive traverser. So for every, if I am traversing the tree, so for going to the every leaf of every level of the tree, I need to ask the server to send the node, and then I can traverse the tree. So if the depth of the tree is log n, then I need to do some log n interaction with the cloud, so I can traverse the index. But now there are some new mechanisms that require that data, there is no need to interactively traverse the index. The cloud can also traverse the index. But both the techniques are suffering from one issue, that cloud cannot update the index. And the another thing is that cloud cannot create the index. So every time user needs to create the index, and update is not possible on the encrypted index. So our focus is on the new part, that how the cloud can traverse the index. So we will focus on a new technique that's called PB tree. So in indexing mechanism, what we need to do? First, we need to create a tree. What a tree will contain? Tree will contain several nodes. So node will contain the values. So what will be the values first? So we need to first see what are the values and how they are creating the nodes of the tree. So first, see just by see this thing with the help of example. Let's say the number is 6, and I want to store the number 6 in 5-bit binary. So the representation is 00110 in binary of representation of the 6. Now I need to create the prefix family of 6. So when I create the prefix family, if I start skipping the least significant bit, so it can cover the entire value. So for example, the first value 00110, it is giving you, okay, this is exactly 6. The second value 0011 star. So star can be either 1 or 0, but I can know by knowing only this part, 6 is there or not. Same thing for the third, fourth, and fifth, and so on. So every time if the bit length is W, I can create the prefix family of size W plus 1. So these things will help me in creating the nodes. So here is the thing that leaf node will contain the exactly prefix family of one data item, and the other node will contain the union of their child node. So suppose these are the numbers are given to the database owner, and he wants to create the this kind of tree. So tree is created in top-down manner. So first step is this: you need to find the prefix family of all these numbers. And if I will give you, okay, I need to represent all these numbers into 8-bit, so I will create prefix family of 9 numbers for each these bit. Then I allocate all these prefix family to the root node. So here is the root node. So here the notation is saying that F1 is the prefix family of 1, F6 is the prefix family of 6, and so on. Since I told you that the tree is created in the bottom up manner, so now you need to partition this entire node into almost equally two parts and distribute the child node. So here is a thing to note. See here, the left hand child may contain the larger values as compared to the right hand child. So right hand child, left hand child is containing prefix family of F16, while right hand child is containing the prefix family of F9. So there is no restriction to maintain this tree like a binary tree. So by this way, you when you reach to the second level, then you will create the third, fourth, fifth. So in this way, we will create this kind of tree. So this tree is created, and before outsourcing this tree, we need to perform some security mechanisms. So first, implementing the security mechanisms, let's see how we can search on this tree if it is in clear text. Suppose I have this tree, and A, B, C, D are showing the nodes of this tree. And I want to search F6, means the number 6. So how can I search F6? So first I need to create a prefix family of 6. So here I create the prefix family of 6, and then I need to find the intersection of the prefix family of 6. If, as you saw in the previous slide, that if I am using 5 bits, the prefix family of 6 will contain 6 numbers. If these 6 numbers will match to 6 number of the root node, then I can know, okay, the F6 is matching, means the 6 number is in this side. Now I need to go to the both side, left side and the right side. When I come to the left and right side, I do the same operation again. So on the node B and node C, I again start checking the entire prefix family, means all the 6 number, and perform the intersection. If they are matching, then I will go to their children. So now see here, this right hand child, the node C, will not contain the entire value. It will however, the node B will contain the value. So I will continue the child node of B. Now I come to node D and E. The same operation will continue, and finally I will got F6. So this node will be retrieved. Now the paper is also suggesting that the same technique can also work for range queries. So suppose the range queries find all the numbers between 0 and 8. So what will be the steps for executing the range query? So first, as we represent the numbers in prefix family, so first I represent the prefix family of 0 and then prefix family of 8. After that, we will find the minimal set of prefix that can cover the entire range. So minimal prefix set is containing only two elements, 0, 0, star, 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 and 0, 1, 0, 0, 0. So if I have only these two numbers, I can find all the numbers because the first number will cover all the number from 0 to 7. So what will happen in the next step? I will send this data to cloud. Suppose cloud is containing this index in the clear text. Now cloud will do the same operation. It needs to search only these two prefixes in the each node. If the intersection is not null, it will continue. Otherwise, it will stop. So on the node A, it will continue. Then it will find, okay, B is containing. It will continue to the B node. It may continue also to the C node, or it may not, depending on the numbers. Then it may go down to node D and E, and eventually it will find all the nodes that are satisfying the range between the 0 and 8. So I will get the value 1, 6, and 7, and I can give this value to the user. But now you saw this entire operation as in clear text. We need to see how we can securely outsource this index structure so that the cloud will never know what are the values. So in order to hide the values, we use two things. First, we use the Bloom filter, encrypted Bloom filter. So we use HMAC with our different keys and encrypt this data to different hash functions. And for now, because since suppose here is a value F6 and F7, the prefix family of these two nodes in the Bloom filter will also contain the same, some values of the Bloom filter will be same for this F6 and F7. Now the adversary can observe that after observing these values, how many values are matching. Based on this thing, he can also observe that what are the orders of the values. So to hide this thing, for each node of the tree, we use a random number. So for a node B, we use a random number VR and include in when we are doing the hash function. So first we perform the hash function using the Bloom filter, and then for each node we perform the HMAC over this part. So the internal bracket that you are seeing, so I will send this thing to the cloud, and cloud can perform the outer bracket operation whenever he is searching. So, but there is another problem, that this technique is secure whenever the adversary is non-adaptive. But whenever the adversary is adaptive, that he can do some reverse engineering, or after observing the many queries, he can also learn the queries as well as the data. So in order to hide this thing, there is a technique that called PV tree, and it modifies all the nodes by replicating some more data. But I am not going into the detail of IV tree. Now we saw how we can search execute a range queries on the tree structure. But there are some other techniques are also developed for executing the range queries or finding the maximum and minimum. They are called the order preserving encryption. So idea of the order preserving encryption is this: if there are two values A and B, then the encryption of A should be less than the encryption of B. That if I compare in clear text two values, then I can also compare two values in encrypted domain. So as this syntax is showing, based on this thing, we can also execute the range query. This paper was introduced in Sigma for the first time in Sigma 2004, and after that several papers have been developed to modify the OPE techniques or provide some security properties. But since OPE is revealing some order of the values, so then there are several attacks on OPE. One of the most famous work in this direction is published in CCS 2015 by Navid, and after that several other papers were developed to find the vulnerability in OPE technique. I am discussing only one of the OPE technique. Are you hearing me or not?
Yes, we can hear you.
Okay.
Yes, Shantanu.
Okay, so this technique is called mutable order preserving encryption. And this is by Popa and 2013 paper in IEEE. So what is happening in this technique? Suppose I am giving you 5 numbers: 10, 20, 25, 32, and 69. So what they are saying that you need to encrypt the data, but you are revealing the order of these values. So the thing that is written not in the gray box, uh, that is the data that I will outsource to the cloud. But I am not allowing cloud to traverse the tree by its own, or he can create the tree. And I define the tree means the database owner will define the tree and he will give the ordering of the tree to the cloud side. So how he will create this thing? So suppose I am first time I am inserting value 32. So 32 will become the root node. Then the next value will come. If 20 is the next value, I will insert the left child. So this is strictly following the binary search tree pattern. Then I will insert 10, 25 and 60. So whatever values goes to the left side, they will be allocated the value 0, and whatever values will be going to the right side, they will be allocated 1. So now see the right hand side. In right hand side, you will see that I am using two colors. One is in blue and one is in the black color. So for the root node, there is nothing. So root node is the square bracket is empty. Now if you see the value 0, this value is representing for the node that is containing value 20. But now if you see the value for 10, this is also containing 0, 0. So the represent ordering of the value 0, 0 or 0, they are same. You cannot distinguish, okay, what is the meaning of this 0. So to make the proper ordering, they paired all the remaining values to the log n side, where n is the number of the record. So here the depth of the tree is 3. So I need to add 3 values in each path if it is empty. So the maximum length of each path is 3. So for the first empty bracket, I add 1 and then 2 zeros. For the next value, I add 1 and then only 1 0 and so on. So in this way, I create the perfect ordering. And if I convert these numbers into decimal, I can see, okay, 1, 2, 3, 4. So I get the perfect ordering. So in this case, I will outsource this ciphertext to the cloud, and I will outsource this OPE encoding to the cloud side. Now cloud can traverse the value. If I am asking any value, he can directly traverse the range or comparison operation. So now see how it can execute the range query. Suppose I want to execute, I want to fetch all the values that are greater than 5. So I need to convert this query. First, I will encrypt the value 5, and then I will find the OPE ordering. What is the OPE ordering of the 5? So for example, just like written here, 4, 2, 6, 1, 3. So one of the ordering I will find of OPE of 5. Based on this, I will ask whatever values you have ordering more than ordering of 5, please send me. Since the cloud can see all the ordering, he will send you all the values. But now here are again, this is suffering some problem, the insert operation. First, whenever you want to insert a value, the user need to traverse the entire tree. And then it may happen, suppose I am inserting first, after 32, I am inserting 69, 100, 200. So that tree is following only one path. The tree depth will increase. This is not a good thing. Then I need to rebalance the entire tree. Whenever I will rebalance the entire tree, then it will take several interactions between the user and the cloud. So it cannot handle frequent data insert operation. So now,
Shantanu, one clarification. You say encryption before OPE encoding. What kind of encryption are you talking about here?
and they are using deterministic encryption.
Oh, I see. Okay.
Yeah.
Okay. Thank you.
Okay, so what we have discussed here, so we discussed two things. First is point query execution and range query execution. And we saw how we can do these queries in indexable manner and non-indexable manner. But now what about joins and other aggregation queries? So first we saw, this is the very old paper by Sharad. So they are creating buckets. Suppose this is the database, and based on this database, they will create the bucket. So for each value, 30K to 50K, they will allocate one bucket ID, for 50K to 70K, another bucket ID, and so on. Now, whenever they are outsourcing the data, they will see, okay, which bucket ID my value is belonging to, and then allocate that bucket ID to that data and outsource to the cloud. These values will be allocated and outsourced to the cloud. Now, whenever a query will come, I need to check the, suppose this is the query, fetch all the employees detail, or employee name, where the salary is greater than 90K and less than 100K. So I need to find which bucket I need to fetch. I will convert this, first find the bucket IDs and then fetch all the bucket IDs that are satisfying my query. But the problem is this, in this case, I will get false positive, means some overhead. The user needs to filter all the useless result at his side. But there are some advantages here that you can execute several types of SQL queries on this data based on the bucket ID. And the disadvantage, user needs to perform some work to remove the false positive. And the mechanism of this entire technique, it depends on the size of the bucket. So if my bucket size is very small, then it is not secure. It will reveal some more information. If the bucket size is very large, then it will increase the overhead at the user side whenever he is filtering. So I need to select the bucket size in such a manner that it will trade off between the security and the cost mechanism. So Murat also wrote paper on the some security attacks on the bucketization techniques. What will happen if the bucket size is very small or bucket size is very large? These are the some advantages and disadvantages of this technique. So based on this bucketization technique, we can do join operation. Since we have the bucket ID, when the cloud can perform the join operation based on the bucket ID. If there are two tables have the same bucket ID, cloud can join the rows of the table and send the result to the user. But again, user needs to avoid, user needs to perform the filtering operation, and he wants to avoid this. So this area of join computation on the outsourced data, this has very limited number of papers as compared to searchable encryption or order preserving encryption. I will show you some papers at the end, but now I will show you one more technique that can perform join operation at the cloud side. But again, you will see that in this case, user is performing some more operation also. So here, consider that there are two tables, T1 and T2. So I represent these two tables into four different representations. One is the row-wise representation, just like normal databases. Then column representation, column-oriented databases. Then value representation and cross-value representation. So they introduced two more types of value representation, value and cross-value. So now see in this figure, this is the way that they are outsourcing the data. So first see the left hand side topmost table, encrypted row multimap. So you will see that it is including T1, 1 and green color box. So this is representing that this green color box is from the table 1 and this is the row number 1. Same thing for the yellow box T1, 2. This is that is representing the tuple is from the table number 1 and row number 2, and so on for table 2. Now you see the second column, encrypted column multimap. In this case, you need to store all the values of the column. So first see that in table 1, the first column name is ATT1. So I wrote it down T1, 1 means that table 1 and column number 1, and there are two values, green and yellow. I stored these two values. Actual value means 1 and 2. For this T1, 2, I store CS and math. Same thing I perform for the second table. Now I create the value multimap, how the values are represented in the database. For each value of the table, I create this multimap. So in this table, just see the fifth row, for example. No, sixth row. The sixth row is saying that 2, T2, ATT3. So now the meaning of this value is that you are representing the value 2 of table 2 that is given in the attribute number 3. So now you can check that, okay, in table 2 is containing which tuple. So this is T2 and T3. So I store these two tuples and make in this part. Now I also perform the join operation at the user side. and this is called the encrypted dictionary. So if I join two operations, let's see T1 and T2. So whatever is the result, suppose I am joining based on ATT1 and ATT3. Whatever is the join output, I will write it here. So see here. Then I can see here that the green color is matched with the blue thing. So I wrote it down T1 comma 1 and T2 comma 1. So now if a query and the database owner will encrypt this thing and outsource to the cloud. They provide some mechanisms to traverse these dictionaries or encrypt in multi-map. Whenever the query will come, they can traverse the entire these code data structure and give me the answer. But so for selection, they use the row multi-map and value multi-map. For projection, they use column multi-map and value multi-map. For join, they use this encrypted dictionary. But now you see that all the things is already computed by the user. So user pre-computed all the things and then outsourcing. So user is performing significant work. This is not good thing that user is performing all the things. Aggregation queries you cannot perform at the cloud side in this approach. For aggregation queries, you need to again download the data at your side and then user can do.
Shantanu, one quick clarification. Does it require you, can you do multiple joins, like multiple table joins with this approach?
Yeah. Whatever tables you want to join it, you can just join at your side, at your local side, create the dictionary and outsource it.
Okay,
so the cloud is not doing join for you. You are doing the join and you are storing this joined output at the cloud side. And you are just fetching the thing according to your selection query criteria. Hello.
Sorry, thank you. I was muted. Sorry. Thank you.
Okay, and third problem is that it can also not execute the complex queries. These are the some papers that are also dealing with encryption approaches. One is based on Bloom filter. The second one is by Arvind Arasu on in ICDT. Then bilinear group based paper. Then the third paper is last year ICD paper. And there is a different approach for verifiable join. But I am not going to cover all these papers right now. So we have seen several things now. First, non-indexable searchable encryption techniques, indexable searchable techniques, bucketization for join, aggregation, OPE, and pre-computed join. But what are the systems that are using these techniques? Is there any one or not? There are several systems. So first, CryptDB and ARC. This is by POPA, and they are using deterministic encryption or some different techniques. Cipherbase, they are using again different techniques. So all these systems are using different techniques. I have slides for encrypted key value store, but since this is the break time, so I am stopping right now here. Is it okay to take break now and then come again at 30 minutes, or should I continue? What is the plan?
Well, how much longer do you have, do you think?
No, I need to continue at least 30 minutes. Yeah.
Oh, okay. If I was just saying, if there's a natural stopping point, then yeah, then
But
maybe
now,
we should break now.
Now I am thinking to skip this encryption part, and otherwise it will take.
I would recommend that. I would skip this part and then go to secret sharing because that'll be more interesting. That's a little bit different. So maybe we should take a break now.
Before the break, let's see the advantages and disadvantages. Then we can take the break. So,
okay, great.
Yeah. So in encryption techniques, so we have several techniques. Deterministic encryption, this is very fast, almost like clear text search. But the problem is this, it will reveal the entire distribution of values. OPE, order preserving encryption, it will allow you to compare the values, but it will reveal the ordering. Searchable encryption is again fast, but whenever you execute the things, it will reveal the data distribution. Bucketization is secure as compared to these three techniques. But now, if buckets are properly created, but now if client need to perform more work, so now some people are starting that they are mixing cryptographic techniques on a single table, just like CryptDB. So they use onion encryption, deterministic encryption, OPE, homomorphic. They encrypt on all the tables. So encrypting these techniques, they are also not secure. they reveal entire data as compared to not using only a single technique. They reveal more things. This is showed by Navid in 2005. So right now the question is this: how can we design a secure index, secure encryption technique? And the another question that is, this is very important question, second question, that all the techniques that are there, the user needs to create the index for indexable search encryption technique. There is, I am not aware of any techniques, and I read several papers and discuss with Sarad and other people also. They, according to them also, that all the searchable, all the indexable encryption techniques, the user needs to create the index, and then update also requires some interaction. So we need to work on this part also, that just user do the encryption and outsource the data, and cloud will do everything. Okay, so now I will start after the break from secret sharing based technique.
Great. Okay. So in that case, then why don't we take a 30-minute break and we'll reconvene at the top of the hour.
Thank you.
For the host, I'm pausing the recording. So
Great.
please remember to restart the recording after
Great.
when the session starts.